This is a volumetric digital twin of the deep Earth. To build a map like this, we are attempting to locate and map physical structures buried up to 10 kilometers underground. As this slide highlights, despite that massive 10-kilometer depth, we still require enough resolution to distinguish individual rock layers that are only 15 to 20 meters thick. We construct this pristine, highly ordered 3D model from a foundation of messy, chaotic surface vibrations. If we look at the raw field records, there is a vast gap between what we acquire on the surface and what we can use. The initial data is an overlapping mess of distorted sound waves. Modern geophysics is a continuous battle to fix that distortion. The entire objective is to mathematically improve the signal-to-noise ratio. Finding oil is a mathematical rescue mission. We must isolate the true wave from overwhelming physical interference to create a target we can drill. Looking at this breakdown of active versus passive methods, we see that before generating any signals, geophysicists first passively listen to the Earth's natural fields. By measuring subtle drops in natural gravity, we can identify deep sedimentary basins. A lack of gravity indicates a thick accumulation of lighter sedimentary rock, where oil could theoretically exist. Similarly, mapping magnetic data acts as a warning system. It detects deep volcanic intrusions that might have burned away the organic matter, telling us exactly where to avoid drilling. But these passive methods only provide a regional, macro-scale picture. They lack the resolution to pinpoint the specific boundaries of an underground reservoir. To map exact trap geometries, we have to switch to active discovery. We need to generate our own seismic reflections. Passive fields tell us which massive basin to explore, but active sound waves are the only way to find precise coordinates to place a well. The process begins onshore with vibro-sized trucks. These vehicles act as generative engines, sending controlled frequency sweeps, usually between 10 and 100 Hz, deep into the crust. On the listening side, as shown in this data acquisition overview, we plant thousands of highly sensitive geophones in parallel lines across the surface. The distance between these individual sensors is critical. That spacing directly dictates the ultimate resolution of our final subsurface image. We rely primarily on P waves, or compressional waves. As detailed here, these waves travel rapidly downward through varying solid rock layers. The method works because of a physical principle called acoustic impedance. When the downward pulse hits a stark density change, moving from brittle shale into dense limestone, a portion of that energy reflects back to the surface, while the rest continues traveling downward. The strength of that returning echo acts as a geological indicator. A strong reflection signals a major transition in rock type, which often corresponds to the top of a reservoir. However, the raw data captured by the geophones is heavily corrupted. It arrives mixed with surface waves and overlapping, distorted echoes from shallower depths. This chart illustrates the problem perfectly. We begin the mathematical rescue mission with raw field records that have a very low signal-to-noise ratio, sitting right around 25%. Generating reflections is the easy part. The raw data remains totally unreadable until it enters the processing funnel. This processing funnel is a computational gauntlet designed to filter out the noise and clarify the physical truth. The first major issue is contamination. Sound bounces repeatedly between shallow layers, creating muddy, overlapping echoes that blur the image of the deep structures below. We strip those away using deconvolution. This mathematical process isolates the true reflection by identifying and removing the false repetitive echoes. At this stage, we also apply static corrections. These adjust for timing errors caused by changes in surface elevation, ensuring all data is measured from a flat plane. Checking back on our progress chart, we can see the resulting improvement. After filtering, we clear the first computational hurdle, bringing our signal-to-noise ratio to 55%. Deconvolution successfully reveals the true timing of the reflections, but the actual spatial geometry of the rocks remains dangerously warped. Raw seismic data contains an inherent geometric flaw. The system falsely assumes that all sound waves bounce straight back up vertically from the point of impact, but deep geology is complex. When a wave strikes a steep fault or sharply slanted rock layer, it deflects diagonally, returning to a distant surface sensor instead. This creates a severe visual consequence. The overlapping, blurred structures form an optical illusion, placing critical geological faults in the completely wrong physical location. To fix this spatial error, we rely on migration, an advanced imaging algorithm highlighted here on the right. Migration calculates the correct angle of reflection. It mathematically shifts every single data point back to its true three-dimensional spatial coordinate. Looking at our chart one last time, this marks the completion of the processing funnel. The data makes a dramatic leap, reaching a highly refined 95% signal-to-noise ratio. Migration is the ultimate step in the process. It transforms a distorted timing map into an accurate, drill-ready spatial model. We now return to the pristine seismic cube. This high-fidelity volume provides a clean workspace for geoscientists. We enter the final phase, structural interpretation. Experts comb through this 95% clarity volume to locate the structural traps where hydrocarbons gather. They begin with fault picking, tracing rock fractures to see if they act as open pathways for oil or solid barriers. Next is horizon picking. Geoscientists trace the horizontal color bands to map the ceiling of specific reservoir formations. This table outlines the ultimate business value of these tasks. For 3D seismic data, the core application is prospect mapping, which allows us to confidently pinpoint the exact well location. This rigorous mathematical pipeline reduces the financial risk of drilling a multi-million-dollar dry hole. Yet a lingering caveat remains. Despite the extreme computational precision, this 3D cube is an algorithmic prediction based entirely on echoes. Absolute certainty requires physically penetrating the rock layer. We have to measure the formation's properties directly from the inside. As the screen notes, that physical validation is exactly what we will explore in the next episode, the Borehole Truth. Geophysical deep imaging brings us to the exact coordinate on the map, but only the